This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
Now you're on the cutting edge of some new stuff with this idea of fiber optic sensing system, this distributed acoustic sensing. I can't even pronounce it. DAS, the acronym's easier to pronounce, but using that to do subsurface and structural sensing. So can you kind of explain how that works and some of the advantages of that versus some of these more traditional methods with geophones and other sensors?
Yeah. So distributed acoustic sensing, or DAS, is a relatively new type of sensing. It's certainly new compared to other traditional ways that we've used in the past to measure vibrations. You know, historically, we record earthquake shaking with accelerometers. We call them strong motion stations. Broadband seismometers, which are good for recording more distant earthquakes. They're quite sensitive instruments. We would use geophones, as you mentioned. They sound like a phone, right? But it's a geophone, so it's listening to vibrations in the earth. So we put these sensors on structures, or we put them on the ground, and we try and measure earthquake waves or waves that we would generate maybe with our trucks. And we use those vibrations to tell us something about the response to this excitation, this dynamic loading. And in our case, one of the things we do a lot of is trying to image the subsurface. We've already talked about that. So the approach right now has been to basically have all of these individual sensors, and we have literally hundreds of them in our instrumentation pool for NHERI at UTexas. And we go out and we put them on the ground in arrays or patterns. But even if we have like 100 or 200 sensors, which is quite a few, when we start to try and deploy them in arrays, we quickly run out of sensors. We can't put them over really large distances while still maintaining what we call good spatial resolution. So the really cool thing about DAS and using fiber optic sensing is that now our sensor is a fiber optic cable.
So the entire cable is a sensor?
The entire cable. And we can lay it on the ground, or we can bury it in a very shallow trench, or we can even hook up to existing telecommunications fiber optic networks.
Whoa.
That might be run by AT&T or Google or whatever. Okay, the same fiber optic cables that are used to carry your internet to your house, your TV. If
so you
anybody
could do something
still has
like
a landline in their home. Okay.
So you could do something like there's I think this was a couple weeks ago where the island nation of Tonga was their fiber optics were completely cut off due to a submarine earthquake or volcanic eruption.
Exactly.
If you had, let's say this was 2 months ago, and you shipped one of your trucks over there, you could have hooked up to the subsea cable and measured the earthquake.
Yeah. So what we would do is we have something called an interrogator, and the interrogator, let's just call it a computer that we hook up to the fiber optic cable. And then that interrogator sends a laser pulse down the fiber optic. And if you've never seen a fiber optic cable or a fiber, it's almost the diameter of your hair. Okay. So they're really, really small fibers, and we send a pulse of light down the fiber, and it travels down the fiber, and it starts getting parts of the light, the laser, getting reflected back every time it sees a discontinuity in the cable. So every little imperfection in the cable is a signature in the pulse of light that goes down and back. And we can then excite the ground, hit on the ground, for example, and it will distort the cable just absolutely minimally. Like you would never ever be able to feel it with your body, your hands, your feet, or even sense it because the strains are so small. But the cable, the fiber optic cable, is slightly distorted, and it changes the pattern of the light that's reflected back and forth. And we can use about every meter along the fiber optic cable we can have, it's like having a receiver. So
Oh, wow.
we could bury a cable in the ground that's a kilometer long, 2 kilometers, 5 kilometers, 10 kilometers, up to 30 kilometers long. And literally we can record a vibration measurement every meter. So now you're talking about 30,000 receivers in a line, or we can bend it and create arrays.
Mm-hmm.
So it's the future of sensing. You can put the cable on structures, you can put it in the ground. Like I said, you can turn existing telecommunication networks into an array of sensors across parts of a city. And it's a really exciting thing. And it makes sense that we would then have this new fiber optic interrogator in conjunction with our shaker trucks, because we use the interrogator to record the vibrations and we use the trucks to generate the vibrations.
Yeah. So you could, let's say if you're building a new apartment building, you could embed fiber optic cable in the concrete and have a structural health monitoring system in your building.
Absolutely. Yeah, you could. And the good news is there's different types of fiber optic sensing that you can even have more spatial resolution than 1 meter. Like for acoustic sensing, right now, the closest channel separation we have is about 1 meter. But if you go to distributed strain sensing and even distributed temperature sensing, you can shrink that down to the order of 10 centimeters or even less potentially. And so you can use different types of cables, fiber, I should say, installed in a single cable. And you can do temperature sensing, strain sensing, and acoustic sensing, all with one cable that you might install in a structure and then wrapping around in the ground, for example.
Wow. My mind is blown. It's just spinning of, wow, you could use it for this, this, and this, and this. Like, so many different applications. Which is going to be good for future research, and any grad students listening out there going, ooh, that would be a really good thesis. Yes.
Yeah, we talk about smart infrastructure, right? Like that's what we want. And fiber optic sensing is going to help bring us into that next era in our field of study, where we're able to monitor our roads, our bridges, our buildings, our dams, our levees, by just having fiber optic cable installed in and on and around these the things I've described, and then using it to measure how well the system is behaving as a function of time.
Wow, that's going to be fascinating to see how this evolves over the years. For those who are like, okay, this is cool, I want to follow along, see what they're up to. Where can people engage with the UTexas mobile shaker team and see what the research is coming out and follow along with where they're deploying and things like that?
Yeah, so we have a website on DesignSafe, and if you just type in Google NHERI at UTexas and mobile shakers, or Texas mobile shakers, our site will pop up. You'll be able to find it. And on that website, we have an overview of our equipment. We have resources, like we have a bunch of, every year we do 1 or 2 workshops related to the science plan, those 3 areas of study that we've talked about. And we have all the recordings from our past workshops. We just did one on distributed acoustic sensing in Louisiana back in October on a levee in conjunction with the U.S. Army Corps of Engineers and UC Berkeley. We've done a bridge testing workshop a few years ago in New Jersey with Rutgers University. We did a workshop regarding the biosoil improvement with the folks at Portland State. And so, like, all of that information is on our website.
Yeah, excellent. Well, we'll make sure to link to that in the show notes. And hey, Brady, thanks for joining today. It's been good chatting with you. And I mean, like all of our sites, it's like, oh man, we do a lot of cool stuff. So it's just It's fun for me as much as anybody listening, just to be reminded how awesome of a team we have at the various NHERI sites, and I just really appreciate you taking the time to chat with us about it today.
Yeah, you're welcome, and we are grateful for the support of the U.S. National Science Foundation to establish all of these really amazing sites. And I agree with you. Every time I visit one of our other NHERI sites, it's just incredible the work that's going on, and really, really cool stuff.
Yeah. Thanks for joining today, Brady. Well, hopefully we'll see you at EERI or something soon, and get together. That'd be great. Take care.
All right. Thanks a lot, Dan.
Thanks for listening to today's episode of Design Safe Radio. This show is sponsored by the National Science Foundation grant number 1612144. You can subscribe to Design Safe Radio on iTunes, Stitcher, or wherever you find your podcasts. Please leave us a review so we can improve the show. Please also help others find our episodes in iTunes. Thanks for your feedback and support. You can find out more about NHERI at designsafe-ci.org, on Facebook at Design Safe Radio, or on Twitter at NHERI Design Safe.